Hey there, I received a request for help with this one, which is 12.1, number 27 in my math lab. This is the study plan, of course, where it shows up in your actual homework, anybody knows. All right, I'm going to do the example, not the actual problem, but it should work very similarly. So according to a census company, 8.1% of all babies born are of low birth weight. An obstetrician wanted to know whether mothers between the ages of 35 and 39 give birth to a higher percentage of low birth weight babies. She randomly selected 350 births for which the mother was 35 to 39 years old and found 30 low birth weight babies. Compare complete parts A through C below. Okay. So if the proportion of low weight babies for mothers in this age group is 0.081, compute the expected number of low birth weights to 35 to 39-year-old mothers. What is the expected number of births to mothers that are not low birth weight? Okay, so let me grab Excel here. So let's do some expectation here. So this is the relative frequency. Okay, so the relative frequency, let's see, low birth weight and not low birth weight. Okay, so let's see here. We said 0.081 is the relative frequency for low birth weight. So this would be 1 minus that. And then we have the expected number. I'll just put that there, expected number. That would be equal to how many births we got? 350 times that value. Drag. Now to make sure this works, you should check that the sum of that is 350. Yep, it is. Okay, cool. So we have 350 births, 321 and a half of them are here, and 28 and some change are there. Okay, so that would be, let's see if we match up. We said 321 and 28. Let's see if that matches what they said. Yep, 321 and 28. All right, what's the next thing they want? Oh, the observed. Okay, so what we actually observed, number, let's see, they observed for this group, does it say somewhere? Oh, 30. There it is. Found 30 low weight babies. So we've got 30 here, which means we have 350. Take away 30 here, right? 320, because you got to get 350 when it's over. We don't really need to know that that's... Oh, I better leave that in there then. That's not going to work. Okay, cool. So we got that part, and let me see. That'll match, hopefully. Yep, 320 and 30. Everything's good there. Now answer the obstetrician's question at the alpha 0.05 level significance using the chi-square goodness of fit test. Okay, so goodness of fit test would be, is that proportion matching what they said it was, right? That it's 8.1%. Or obstetrician wants to know whether higher percentage, see that? So the obstetrician wanted to know whether mothers between the ages of 35 and 39 give birth to a higher percentage of low birth weight babies. Higher, so it's a right-tailed test. So we assumed that it's 8.1%, and then higher would be greater than 8.1%, or 0.081. Okay, so then this p-value they come up with, let me show you how to do it. So I'm going to take my data, observed and all that stuff. I'm going to go paste it into StatCrunch. So let me grab StatCrunch. And I have in here an old problem. That's fine. I'll just put it over here. Actually, hold on. Let me clear all this out. There. I didn't want you to get confused. All right. So we have our low birth weight. We are not low birth weight. I just called it weight. I just put, and I should probably put that over here, but weight. There we go. Okie dokie. So we're going to go to stat, goodness of fit, chi-square. And let's see, our observed was in the observed number for us. Our expected is in the expected number. Click calculate. And we get a super high 0.7465. Let's see if that matches. Or if I did something wrong. Nope, 0.746. That's what they got. Cool. Okay, so that's how you get your p-value with the chi-square test. All right, then they want you to do it over again, but with what we learned in chapter 10, actually, which is using the normal distribution, right? In other words, instead of doing this as a goodness of fit, because there's only one proportion really, see, goodness of fit works really great when you have multiple proportions. But when you have a single proportion, you could do goodness of fit, or you could do the z-distribution approach, which we learned in section 10.2. So if you go back to that. Okay, so let me grab that. This would be the same null and alternative hypotheses, right? Because it's still the proportion is greater or than 0.081. So then let's go to StatCrunch, and let's do this. Proportions from a one sample. We have a summary. So how many successes did we have? Well, that would be what you actually observed in your real problem, which was 30 out of 350, right? Because 30 low birth weights, which isn't a good thing, but it counts as a success, out of 350 total births. Okay. Now we are trying to test the null hypothesis of 0.081, and we want a greater than test, right? Because we're doing a right-tailed test. Our null and alternative hypotheses were equal and greater than. All right, so let me go back here and then click next. I don't need to store it. Calculate. Look at that, 0.373. And that's what they said it was right there, 0.373. By the way, both of those tests have ridiculously high p-values. You would not reject, right? Remember, we reject when our p-value is low, and these p-values are not low. So we will not reject the null hypothesis, which means this researcher didn't have enough evidence to prove that this proportion of low birth weight babies is greater than 0.081. All right, I hope that helps.